All right. Hey, everybody. Hope you are all doing well. Last week of class, so hopefully that is a positive for most of you, anyway. Um, I have posted the final presentation comment, or I guess requirements, in Blackboard. Keep in mind that it's basically intended to be kind of an extension of the midterm. Really, what I would like it to be is kind of a show me show me and your classmates the really cool thing that you did throughout the semester. Obviously, there are some key beats that you have to hit to, make it a graded assignment, but I really want it to be kind of something, fun and not super stressful for all of you. So key points, let me zoom in a little bit. Shouldn't look too much out of the realm of possibility for you all. It's in the term project, and for some reason, Blackboard is just not being nice with their ordering for me. Apparently, I noticed there's a bug that's actually been mentioned about that. But who are you? Again, we should know who you all are at this point and what your project is, but let's reintroduce ourselves. Um, Basically, did you hit your timing goals? So you had to come up with that timing diagram. Did you meet those goals? What has changed in your project since the midterm, too? So we had our midterm. What have you done since then, basically? And talk about your testing strategy. So, like, what are the areas you focused on? Maybe did you do something interesting with your testing strategy? Um, are you doing it manually, automatically, those kinds of things? And then show us what you did. And because I know a lot of you are doing interesting applications or games or things like that, and I've kind of been forcing you to put it all in GitHub, that means that everybody should, in theory, be able to download it and run it if they want to. So just a little overview of how it all kind of works together, like what somebody would need to know to get it up and running. But that is the final presentation. Basically you've got deliverables for this. So the presentation, I want your PowerPoints or your slides, PDF, whatever you have. Deliverables, we should know already. I'm also going to put up a short write-up assignment of um, like a self-reflection kind of a thing, where I just ask you to write a short little paragraph on your term project, your teammates, basically evaluation type of thing. I will probably make that due before next week, Friday, just so that I have time to um, read it over, basically. The rest of them should be pretty straightforward. That one I have to kind of dig into. And right now I'm working on grading your last two homework assignments. I really need to start making grading easier on me so that it doesn't take me a year and a day to grade things. But um, homework 5 was kind of a big thing to dig into. So, questions at all so far? Is everything fairly straightforward, hopefully? If you just joined, looking for the summary, presentation, information's been posted. Don't forget about your deliverables, and you have a short little writing thing coming up soon to, I guess, plan for, but shouldn't take you that long to write. More personal reflection rather than hard software engineering work. Okay, otherwise, let's get going. What we are going to talk about today is we're going to go further into verification and validation. So last time we kind of talked about things at, again, kind of a high level, testing strategies, testing levels. Today we're going to talk about some different actual ways to do testing, verification or validation, basically. And it should be a little bit interesting. Basically, to me, um, exciting and fun and interesting, but obviously to most people, testing is going to be a slog. Um, but it's a very necessary part of the process. But what you're going to get out of this hopefully today and Wednesday is how to actually perform some of these tests. Then we'll talk about some debugging techniques as well. If you discover failures, what do you do? Probably won't get to this until Wednesday, honestly. But away we go. So before we talked about black box and white box testing, right? Or black box and white box modeling. Again, these terms are going to keep haunting you throughout the entirety of your CS, CE, whatever your degree is career. Um, Again, if you remember black box, you only care about the inputs and outputs. You can't see inside the box. White box or glass box or whatever your favorite transparent material is, you can see inside, meaning that you're testing the algorithm. Okay, and for testing, what does testing the algorithm mean? That means looking at the paths of execution, making sure the expressed behaviors are correct, not just looking at the inputs and outputs of your thing, right? Your class or your program or your function, whatever you're looking at. So here we've got a few techniques we're going to be talking about. In black box, we're going to be looking at equivalence partitioning and boundary value analysis. These are basically ways of figuring out which values to test. And then the white box side, coverage and basis path testing, is going to be looking at which paths of execution are you following, right? Are you going down the correct branches? Are you checking to make sure that every single if statement and else case has been covered, every single switch case? If you have any kind of recursion going on, are you bailing out correctly? Are you running it the exact number of times you want? So things of that nature. Basically, again, black box, we only care about values. White box, we care about the actual logic behind things here. All right, so black box, you may also hear of this in your future career as an engineer as functional testing, behavioral testing, somewhat interchangeable words in a way. Effectively, you're just checking to make sure that what you're testing is following what you've written in your requirements or whichever artifacts you're kind of tying yourself to with these test cases. Now, this is something that can be done at any stage, tends to be done later on. So basically, when you're doing your integration and beyond testing, so you're starting to put things together. You might be linking modules together. You might be doing whole system testing, customer acceptance testing. Here again, we're kind of just caring about this package that you've nicely tied up and maybe you're delivering or integrating, and you want to make sure that it's doing what you say it should be doing. Yeah, because that's all testing really is at the end of the day. Are you doing what your requirement spec says you should be doing? That doesn't mean that that's correct or the right, but you're assuming your requirements are good because hopefully by this point you've kind of verified that yes, they are correct. But that's all you really can test yourself to, right? You don't have a golden magical rule that says these test cases are always this. This is what your requirements say. Your test cases support that. You're kind of providing evidence. So what do we care about here? Obviously, values should match, but you can also get out of this. Maybe you have a problem with your interfaces, right? So if you're bringing together modules, there might be some miscommunication at the interface level, right? Maybe I'm calling another module's function incorrectly. Maybe I'm, passing in bad values, values that are out of range. Maybe they're the wrong data type and they're being kind of squished down into a different format. Basically, all of these kinds of things that may manifest when you start bringing different pieces together, right? It's not just going to be you working on a project, it'll be you and a large team or you and a team of some sort. So if you don't necessarily understand somebody else's module or maybe it's not well documented, there's a very good chance you can have these kinds of problems. And maybe there's a missing function and the compiler just isn't catching it. Um, it could be like a Python project where it's interpreted and you don't discover that until you actually try to run that block of code. Maybe there's a performance error. Your program is running ridiculously slow because you forgot to deallocate memory. Right? Like you load a bunch of images into memory. Those of you doing Unity or Godot or any kind of game, you load in all your millions of sprites or textures all at once, and then you keep loading them in over and over and over again, and then things start to slow down. Probably wouldn't catch that at the unit level, but maybe when we're trying to do functional testing and make sure everything is doing what you say it should be doing, that's when you start catching it. So again, this is kind of the black box level here. Sorry, my phone buzzed and I'm trying to see what's going on. So, black box hopefully makes sense. Now let's actually talk about some of these methods. So if you remember from 2 classes ago, I can count, um, we talked about exhaustive testing, right? That's where you are checking every single possible value. And we said that is pretty much infeasible, if not impossible, right? Because you get to that exponential level of here's all these values. The more things you add in, the more you have to test, the more combinations you get up into the hundreds of thousands of years of running sequential tests, and it's just not going to happen. We talked about systematic testing, where you try to be kind of intelligent about what you're testing, right? You don't have to test every value because you can pretty much guarantee they're all going to be relatively similar in a particular area, right? So this is what equivalence testing, equivalence partitioning is doing. Basically, we are trying to kind of zone in on a class of data where we know that if we put something from this range in, we will get a certain output. Now, it's not always going to be the same answer, right? If you're testing like your addition function, you know that the range of all positive integers will probably add correctly, right? So you don't have to test 1 plus 2, 1 plus 3, 1 plus 4. You can just test 5 plus 10, and that might be an example out of that equivalence set. So effectively, you know what let's take the mathematical operation example. Basically, if you have two numbers that have a mathematical operation being performed, you know that x plus y will always equal z, or x times 5 to the power of y remainder z, whatever your function is. You can figure out what the output should be, right? So you know what the answer will be in this case. You don't have to exhaustively test every possible combination because you can get a representative set of data and get kind of a good enough idea of what the behavior of your program is going to be. So hopefully that kind of makes sense. Basically, you're just partitioning your data set, partition your input data, partition your output data into known sets of information. Now, are you going to get every single error with this? No, but you can kind of zero in on what we'll call classes of errors. So you know that if you start seeing like oddities with, maybe an addition operation, maybe your exponential operation, or if you're dividing things, you realize that when you're dividing two numbers, maybe it's casting them to floats, and you are getting some kind of weird information back where you're expecting an integer or a character or something. So basically, you're just trying to zone in on particular problems, and then you would go further in and kind of see what's going on. But think of testing at kind of a broader level in a way. Make sense, more or less? Is that all we've got there? Yeah. So basically, just to look at your data, and again, this is black box, so we're looking at input versus output, and you don't care what's happening inside the box, right? If you have data coming in, you can probably categorize that data into some, larger category. Maybe it's integers, maybe it's integers on the boundary of where the integer max is, right? So 2 to the 32 or 2 to the 64. Everything in between this range is fine. When you get out to the boundary of how much of a value you can hold, then you might have a different class. Because if you start adding large numbers together, maybe it rolls over and you get really weird stack problems or something like that. But here would be an example to kind of really demonstrate this. So here we want to figure out, somebody's entering their age into a text box here, right? So we are expecting people using this application to be between 18 and 56 years old, right? You can't be a youngin, can't be an olden, I guess, elderly. But equivalence partitions here would be the valid range, so 18 to 56, inclusive in this case. And then the invalid ranges would be less than or equal to 17, greater than or equal to 57. So here we basically have 2 or 3, depending on how you want to structure it, equivalence classes, right? So you know that any value between 18 and 56 will be fine here. You don't necessarily care what that's doing inside. You just want to make sure, is this value good or not, right? If you're less than or equal to 17, you should see an error pop up in your application. That would be another test case that you would write. Greater than or equal to 57, similar error, you are too old. Apply that to me probably. So basically here, you've got, again, 2 or 3, depending on how you want to classify valid, invalid, or invalid too small, invalid too large, however you want to structure it. But three representative classes of data. Here's another one, mobile number. So your telephone number has to be 10 digits long, right? So a valid case would expect a number that has 10 digits. You don't necessarily care in this case what the values are. You just know it has to have a length of 10 characters. Invalid, maybe it's too large, maybe it's too small. You could extend this to, say this again, this is a phone or a web application. You have international users trying to add in their numbers, and they're going to be much longer than 10, right? You're going to have the country code and all of the other digits attached to it. So, again, idea here is dividing things into representative sets where you know, or at least you think you know, all the values in a particular set will yield some deterministic value that you can check. Does that make sense, more or less? Hopefully, anyway. Again, this idea with equivalence class partitioning is a systematic testing approach. Thank you. Basically, you're trying to reduce the amount of testing that you have to do. So here would be another example for you with a more, kind of an algorithmic idea. So let's say that you want to create a factorial. So you write a function. It's probably going to be a recursive call. Those of you, I'm going to assume factorial is something that you do when you learn recursion. But what do you do with factorial? Normally there's an input. You have an expected output, which is the factorial of your input. And for this case, we're going to bound it between 0 and 25. Okay, so anything larger than 25, we don't want to calculate. Maybe it's too large for a system or something like that, but whatever the reason, 25 is the upper bound. All right, so we have an input, we have an output, and then we have our constraints or our conditions for what the input should be. And here you could generate test cases pretty easily, right? What are our equivalence classes here? Class 1, n is less than 0. Again, makes sense. It can't be less than 0, otherwise this won't work. Maybe we have a hard-coded factorial function or something. All right, so that is class 1. Class 2, n is within a valid range, so between 0 and 25. Any value between 0 and 25, we should be very, we should easily be able to check that the output is that factorial. Class 3, n is greater than 25, so it's too large. Again, it doesn't matter if it's 26, it doesn't matter if it's 300,000, you will get the same invalid error message based on something out of this set of data. Right, so that's really kind of all there is to equivalence partitioning. Honestly, it's more understanding your data set, understanding what the possible inputs are, understanding the possible outputs, and realizing that you can, again, kind of classify sets of data to reduce your testing time. So again, take factorial. If you did exhaustive testing, this would take probably forever to run, right? But we've taken an exponential number of test cases and basically reduced it to 3, right? That's a pretty good cost savings in terms of time, in my opinion, time and effort. So that would be, one black box testing technique. The other one we're going to talk about, assuming that makes sense, and again, feel free to pop in any questions if you have any. To me, it should be fairly clear. We have boundary value analysis. So kind of a similar idea, but it's kind of intended as a complement. So here, with boundary value, you're not going to pick like any random element out of a class. You want to check the bounds of your particular function. So if you have, say, a left and a right boundary for your data, right? So in this last example here, the left boundary would be 0, the right would be 25. Instead of picking like n equals 10, you'd pick values close to those edges. All right, so this will help you find some of those little oddities with that always seem to pop up with like edge cases, basically. All right, so basically what you're trying to do here is you're going to figure out what these boundaries are, and you're going to write test cases that check the exact value, the value that is just above, and the value that is just below that edge case. So go a little bit beyond and a little bit in the actual range. So let me kind of throw everything out here because a lot of text on screen at once. Um, but basically what you're trying to do is there's always going to be issues with that edge case, right? So if you have a integer range or a floating point range or something like that, or maybe you're checking the range of an enumeration, um, there's probably going to be the the chance where maybe you do a greater than instead of a greater than equals. Maybe you're lopping off decimal points and you're not realizing it. Basically, there's always going to be more issues at the edge cases than in the middle of the set. So what BVA does here is it tries to kind of zone in on those aspects as well. And what you as programmers are probably doing is that you're going to do boundary value analysis just kind of out of be I guess practice or experience. You're probably going to intuitively know that that's where all the problems are. So you're going to kind of focus your testing, whether it's just debugging or something like that. You'll probably be checking those edge cases, right? I've got a figure for you here, which should hopefully be helpful. Um, how do you misspell boundary here, but not here? Okay. So let's take this as our equivalence class example, right? So let's say that this is 0, this is 25. Here we have one equivalence class here, less than 0. Equivalence class 2, 0 to 25. Equivalence class 3, greater than 25, right? So that would be your equivalence class. We have these three sets of data that we're checking. Applying boundary value to that means that we would have test cases just outside of that particular edge case and then at the edge case, right? So again, you're checking those boundary values. So I guess before we go to that, this makes sense, hopefully. So take what we did with equivalence class and add a few extra sanity checks to them to make sure that you're not off slightly. Right, with integers, this is probably easy, right? Maybe you forgot a greater than or equals and you wrote greater than. But think about when you're checking, say, floating points or memory addresses or something with a little bit more detail to them. It's a lot easier to have problems here, right? So if you're checking floating points, you can't just do you can't just do equals equals because floating points are always going to have a little bit of margin of error and they're always going to be slightly off. So you have to do like greater than 3.14159,626. I don't remember the rest of pi. And then less than 3.14159,7 or something like that. So you have to check those boundary values. So with boundary value, with equivalence class partitioning, this kind of begs the question that you are intentionally ignoring possible test cases, right? So I'm just telling you, check one, check two, check a small handful of values in your various classes. Do we have to worry about any of the other ones, right? Because we're no longer checking every single possible combination. We're checking just, does this work? Does that work? Okay, it's good enough. Do we have to worry about any of those other values? Because this is kind of the question you have to ask yourself if your test strategy is successful or valid, right? You are not testing everything now. You don't know what happens with a particular value of X or Y or A or sprite sheet dot image. But I'm curious, any thoughts here? I guess if the question doesn't make sense, let me know as well. Not sure if this is slow or if just people aren't here. Yeah, I need a Dora the Explorer emote to add in. Haha, there we go. Thank you, person. Anonymous person, since I can't see who entered them. Let's see. Sure, that's a good one. The puppies are looking at you. All right. Yes, we still need to make sure those values output correctly, but we don't need to test every value. That makes sense, right? If you write your test correctly, you should cover reason, no reason. Yeah, ideally, right? So this is the ideal situation. Yes. No, not right now. Daddy's in class. Can you go downstairs, please? Bye. At least she whispered this time. Um, Basically, the answer here is yes and no. If you are doing equivalence test or boundary testing correctly, you probably are going to be checking like internal odd edge cases anyway, right? But there is always the possibility that something goes wrong inside of your equivalence class. And this could be because maybe you didn't write enough test cases or you didn't understand a particular boundary that exists there. It could be impacted by some other module that's coming in. It just kind of depends. Um, but this is where really understanding the behavior of the program and, again, understanding the intention of your requirements kind of comes into play. So it's one of those yes and no questions where it should be fine. However, there's a chance that something exists that you're not accounting for. That's why having a good solid testing strategy is kind of a good idea. All right, so 2 examples of black box testing. Um, 1 second here. All right. Had a student not paying for the class in here. All right. All right, so white box testing then. This is going to be the other side. There are many other black box testing techniques too, I should mention. It's not only, equivalence and boundary. There's a ton of them. Those are just kind of 2 examples that you'll probably experience or that you're already doing unintentionally or intentionally. White box is going to be checking the internals of your program. So this will be considered more of a structural side. Could be behavioral if you're looking at algorithms, but basically you're testing how your program is actually structured. You care about things like branches in your code. You care about um, is are your loops running fine? Are all the conditions that you've written into your if statements, do those work? Again, recursion. Basically, you're checking the internals of your program here. And this gets a little bit more complicated than black box. And I say that because black box, again, you're just checking inputs and outputs. Whether it's some, formatted value out of a math function, or you're checking performance or something or something or something. Basically, you have a set idea there. White box, checking the actual internals. You need to know a little bit more about the program, basically, which is intended by its name. So first and foremost, let's talk about coverage. And I forgot I was going to have an example for this, but I don't have it. Basically, you want to make sure that every single X is going to be covered by some test case. So let me pop open all of these just to kind of talk about them. So we might care about line coverage, right? So is every single line of code executed at least once? And what that means is that you've written your test cases in such a way that you know that every single line of code has been run. Now, let me maybe hide these so we can talk about this for a second. That is almost an idea of exhaustive coverage from a white box perspective, right? And the key here is that if you have lines of code that are never being executed, what does that mean? Why do you have that code there? What is it doing? If you have some very bizarre edge case that only triggers this one line of code, well, what is that edge case that triggers it? Right? So basically, the line coverage here you should be understanding how to make every single line of code run. And if you, again, have dangling code, that's either going to be a pointer towards some kind of a weird problem, some kind of a bizarre edge case or boundary case that you've never accounted for. Um, or if you have accounted for it, you should have a test case that accounts for it, right? So that's one way to do that. Simple programs, line coverage, pretty easy to attain. Very complicated programs, lots of classes, lots of relationships. Sometimes that line coverage gets a little bit harder, to attain full 100% coverage because there's, again, so many moving pieces there. So, but again, you can kind of consider that almost to be your, not quite, but somewhat akin to your exhaustive testing for the white box version. So, um, I just thought there's something else I wanted to say about that one, but I don't think so now. So the next one then is going to be branch coverage. So here you're looking at your various branch conditions, right? Again, you know the internals of your program at this stage. So you know that if you have an if statement or a switch, or if you're feeling masochistic or sadistic, it could be a go-to statement. Um, but basically you want to make sure that every branch is covered. Now it doesn't have to be every single line, but you should have test cases that basically are exercising each possible path of execution. Right? So if I have an if statement 500 lines down, I should have a test case that triggers that particular branch. And then I should have another test case that triggers the other branch. And it goes back towards that untested code. You should be exercising your program basically. And then what happens when you go down that particular path? With that, we also have condition coverage. So it's kind of similar to branch coverage. Basically, you want to check the various conditions of your if statement. Right? So if I have, an if statement with like an and an or, and you could chain multiples together, basically you're checking each possible instance of that condition. So basically you're almost doing like an equivalence class type of testing with your conditional coverage. And then you can merge those two together. So basically make sure that your conditions all have a check, make sure that you go down each branch appropriately. The last three are kind of all very similar, honestly, but basically you're just making sure that your different paths of execution are being accounted for. So you want to make sure that your code is executed, is kind of the takeaway there. So hopefully that makes sense so far. We also have multiple conditions. Sorry, losing my cursor here. Trying to see if I copy and pasted something wrong. But multiple condition coverage, let's just consider that an extension of normal condition coverage, where effectively you have, again, I kind of mentioned ands and ors, and I jumped the gun a little bit there. If you have more than one condition, you should be exercising all of your various conditions. Here we have conditional coverage, make sure that each condition is covered. Here, if we have multiple conditions, make sure that all conditions are executed. So again, we're just trying to make sure that every path of logic is executed here, if that makes sense. Realize I kind of jumped ahead in what I wanted to talk about there. But make sure that you're checking all of your cases. If you have an if something and something, check the first block, check the second block, check them together, check them empty. Just make sure that all possible conditions are accounted for, basically. You don't want to have some odd condition being expressed at the customer level where, oh, we never checked that condition. Right? And again, conditions are going to be decision logic, right? Your if statements, your loop constructs, switch statements, so things of that nature. Then the other side of things is going to be path coverage. And this is where we start getting into a little bit more detailed calculations. But you basically want to kind of follow the path of execution throughout your program. And this is where we start talking about programs as like graphs. So basically you start here and you kind of move around and then you end up here. Basically, take your program logic and you turn it into a visual graph. You want to make sure that every possible path is covered. Now, you can generalize a little bit here. Some paths are going to be fairly identical, like with your equivalence classes. Maybe some condition always leads to this path of execution. So you only have to check one or, a couple instances of that. But basically the idea here is to just, again, exercise your program, make sure that you are checking everything, that everything is being executed. Again, if you have unexecuted code, you have to wonder why you have unexecuted code. Now, the thing with loop tests, or sorry, path coverage here, is that it is very easy to get into kind of a rut where it's a very infeasible thing to check. Start adding loops or recursion. Um, Basically, if you're taking away an upper boundary, path coverage can become very difficult, computationally and mentally even. So you basically just have to add some bounds here. That was kind of some of the white box techniques at a high level. Obviously, we didn't talk about the particulars here. We're now going to get into basis path testing, and we're not going to get all the way through this today. But this is where we start actually doing some calculations. So if you need to pay attention, now's the time. So with basis path testing, again, white box testing techniques, so we're checking the structure, checking kind of the algorithmic logic inside of something. We need a measure to figure out how complicated a program is. So basically we've got, I think it's going to be 3 formulas that we can use. We're going to see that we get the same value for all of them here. But we're going to use this notion of cyclomatic complexity. So it's a very big software engineering term here. Basically, you're just trying to figure out how many execution paths there can be in your program. And if you can figure that out, you can design test cases around that. And again, to circle back, why are we doing this? Why are we calculating out how complex a program is? Well, you can take that number and figure out which test cases will trigger each path of execution. Right, so if I have a fairly simple program, maybe I get a cyclomatic complexity value of 3. What does that mean? Well, 3 is going to be how many unique paths of execution there are in our program. Right? I always know that I will go down this path, or this path, or this path. Think of it like you have one program with an if statement where you have if, else if, else. Right? That's 3 paths of execution there. We would get a cyclomatic complexity of 3, meaning that we have to design test cases to trigger these 3 paths of execution. Obviously, complicated programs, that value is going to be a little bit higher, right? Simple programs, it'll be smaller. This is, again, informing which tests you have to create. So what do we do here? First and foremost, we are going to take our code, again, your beautiful Java or Python or Lisp or emoji code, and you're going to draw something called a flow graph. Now, this is going to be, I've got the visual on the next page, and I'm hiding some text here, but just says basis set. But basically, this is going to be a visual of the paths of execution. After that, you're going to figure out the cyclomatic complexity, which is this value, and then we're going to basically kind of extrapolate from there. So what is the basis set, which we'll figure out which test cases do we need to exercise that. So first and foremost, let's, I guess, shove me over slightly here. Didn't want to be doing that. Let's take a very simple program for summing some numbers here. Right, so I've got a function here. And again, I should mention too that this can be at a whole program level or a function level. It just kind of depends on what you're checking. Right, maybe I'm just checking a single module and I want to do this whole process. So here I want to sum some numbers. Right, so we're basically going to sum up to a value of n. So start at 1, our sum is 0, while I is less than or equal to n, increment our sum by I, increment I by 1, return the whole sum at the end. Right? Pretty simple program. You have an input parameter of n, we have a while loop, and then we're going to return when we're done. But you say, professor, don't know why I did that. Point at the camera. So we have a condition that we have to check here, right? So we have this while loop where it's checking if I is less than or equal to n, continue, else, bail out and finish the program, right? Straightforward, basically two paths of execution here. Now, if we're going to draw a flow graph, what we would do is we would start when we actually begin like doing things in our program or a function here. So declaring variables we're not really going to count, doesn't really, take any effort. But we're going to start from our assignments, right? So here we've got our function. We have our variable declarations. Ideally, they're at the top of the function, do it C style where you can only have them at the top. We start here. So this is this is line 1, line 2, line 3, 4, 5, and 6. So we'll draw our flow graph. We start here, line 1. This is I equals 1, sum equals 0. Then we go to our conditional here. So if I is less than or equal to n, we're going to say that's true, go down this path. Well, what's 4? 4 is update the sum, 5 is update our iterator, and then go back to the loop. So we have a loop here, kind of angularly drawn, but we have a loop condition, right? So keep doing 3, 4, and 5 until this condition no longer meets, or is no longer valid. Once this is false, go to 6. 6 is return sum. So this is, if you've never seen a flow graph before, you are taking your program and turning it into a visual representation of how things are executed in order, right? And here you can have things like loops, you can have conditionals, you can have branches and all of that. And what we care about, honestly, from a testing perspective, is every single path of execution covered. And coverage is having test cases that trigger that path. So what would a test case here be? We've got two paths of execution, right? So we're going to go 1, 2, 3, 4, 5, 3, 6. 1, 2, 3, 4, 5, 3, 6. That would be one path. The other path would be 1, 2, 3, 6, right? So we might have a case where I is going to be greater than n. How would that happen? Well, if n equals 0, right? So if we pass in 0 here, I is 1, n is 0, I is going to be greater than n. We're not even going to go into this loop. So there we have two ways to trigger this path, right? Make sense so far? Any questions on creating a graph like this? I should say this is one of the simplest types of graphs that you can have. You can make this way more complicated too. Um, do this. Does turning code into a flow graph make sense? Because this is one of the important aspects here. Everything hinges on this idea of paths of execution. I guess if everybody's still awake. Yes, it makes sense. Thank you. Appreciate the response. Awesome. Okay, so if we have that, what do we do now? We have to figure out the cyclomatic complexity. Ooh, it's all in caps. Yelling from the back of the room. I like it. So we have our graph. Next step is to figure out the cyclomatic complexity. This is where we actually have a equation to fill out. Again, this is going to be a measure of how complicated a program is. And we're going to use this value to tell us how many paths there are that are independent. Basically, again, for this one, we'd expect to see 2, right? I think 2. Make sure I said this right. We'll get to that. So basically, again, I'm losing my train of thought here, sorry. We're just trying to write test cases to exercise this program. We're going to do that based on this value of cyclomatic complexity. Now we have 3 ways we can do this. We have an enclosed regions method, the edge node method, the predicate node method. Basically, these are just 3 different ways by looking at this graph to calculate ideally the same value. So first one, enclosed regions. This is where we have a complexity, so let's call this V of G, is going to be ER plus 1. What is ER? ER is the number of enclosed regions. What is an enclosed region? Basically, it is a loop. So it is an area in your graph that is basically enclosed in some way. If we go back here, how many enclosed regions do we have? One, right? So we have this loop here where it is enclosed by nodes and edges. So thing I forgot to mention, circles are nodes, lines are edges. It's a standard graph terminology. But if you're not familiar with that, you should probably mention it. So cyclomatic complexity using this method is to take however many regions you have and add one. That's your complexity. So for a graph, that'd be 1 plus 1 is 2. Again, we have 2 paths of execution. Hey, our complexity value is 2. Again, for a very simple graph, you can just kind of look at it and say, yeah, that's 2 paths. But keep in mind, control graphs can get extremely complicated, and sometimes a method like this is very helpful to calculate that out. So the second method is the edge note method. Basically, you're going to take the number of edges, you're going to take the number of nodes, you're going to subtract nodes from edges, and then you're going to add 2. All right, so very simple formula, but something that you could mathematically perform. The third one is going to take the number of predicate nodes and add 1. What is a predicate node? Well, that's where you have a node with 2 or more edges coming out of it. So think of a conditional, basically. If this, true, else false, right? So that would be a predicate node. So if we go back here, predicate node would be this 3 here, right? Because we have 2 possible paths coming out of it. None of the other nodes are predicate nodes because we don't have 2 leaving. Then you might ask me, well, what about, well, I guess that's just kind of drawn funny. But basically, it's 2 or more leaving, 2 or more edges leaving that node. Now, do you have to memorize these functions? Not necessarily unless you're doing, coverage testing or, I guess, basis path testing a lot. But it's good to kind of keep in mind that there are multiple ways to do this. So let's go ahead and walk through the example here, and then we'll end for today. So enclosed region, cyclomatic complexity is 2, right? Number of enclosed regions, 1 plus 1 is 2. Again, this is our enclosed region here. We don't count the declarations again, just if you need the summary. Edge note, e minus n plus 2. So how many edges do we have? 1, 2, 3, 4, 5, 6. So 6 edges. How many nodes do we have? 1, 2, 3, 4, 5, 6 nodes. 6 minus 6 is 0, plus 2 is 2. You get the same value. Third predicate node, how many predicate nodes do we have? Just 1, right? Because number 3 here has a true or a false. 1 plus 1 is 2. So regardless of the function, we have a cyclomatic complexity of 2. And again, just to reiterate why this is important, this is telling us how many paths we have to figure out how to test. This value is not telling us how to get that. It's just saying, here's how many you have to account for, right? So I think what we will do is we will end there and pick up on Wednesday. Any questions at all from today, or anything that you need to ask before we end class? I should mention too, there are automated tools for generating these graphs. I know the Clips probably has it baked into it. You can generate it in Python or C or whatever your favorite language is. There are tools for automatically generating graphs like this. But it's also kind of a nice thing to understand how it works too. Alrighty. Well, other than that, I will see you all on Wednesday, and we will be that much closer to final exam week. So I hope you all have a wonderful day. I'll see you Wednesday. Bye, everybody.